So in the last lecture, I was trying to tell you that the calculation of certain matrix elements are very complicated in lattice QCD because of the breaking of rotational symmetry that introduces power divergent mixing. So let's so for that I will go through now slides as opposed to my handwriting because perhaps it's easier to look at certain equations that I don't have to write now. So again, what we try to do in lattice QCD is to compute the hadron of the structure of hadrons from first principles using the underlying theory of quantum chromodynamics. And why is this important? It is important in many ways, but if you want to understand high energy scattering, you have to experiments like the ones that happen at Jefferson or at the future EIC. If you want to discover new physics because you use protons as your target in high energy experiments, you need to understand its structure. But also you can ask fundamental questions about hadron physics, such as the origin of mass, of the spin, mechanical properties of the hadron, confinement. These are fundamental questions that you can ask by studying hadron structure. And here is a schematic of what I alluded to in the previous lectures. We have various ways of probing the hadron, the structure of the hadron. If you do elastic form factors, electromagnetic current interaction, as we talked before, you can obtain information about the charge distribution, for example, of the hadron of the inside the proton. In fact, you can only the electromagnetic form factor has an interpretation as a charge density only in the infinite momentum frame, in a sense where the hadron is Lorentz contracted, and you can only study the transverse charge distribution. But that's a technicality. The fundamental the fundamental property that you probe with elastic form factors is a distribution of matter inside the proton. Now you have the deep inelastic scattering, where you can understand the longitudinal momentum fraction distributions of quarks inside, or partons inside the hadron. In this case, let me see, is there a pointer that I can be using? Gone. So in this case, on. I need only here it is, laser. That's fine. So so in this, when these parton distribution functions, which are probed in deep inelastic scattering experiments, they look at the distribution of partons inside the proton as a function of their longitudinal momentum fraction. If the proton is traveling with some high momentum, x represents the fraction of that momentum that is carried by the parton. And this generalized parton distribution functions are an augmented version of parton distribution functions, where you have both the x dependence, the longitudinal momentum fraction, as well as some transverse structure information about the hadron. Now, what allows us to separate the high energy scattering experiments into something that is low energy, which is you have to compute it non-perturbatively from the underlying theory, are the so-called factorization theorems. For example, when you look at an elastic scattering of the proton, you have an interaction of an energetic photon with the proton, and you can factorize the interaction of the quark with the photon from the interaction of the photon with the proton. And this object that I have drawn here as a blob is the electromagnetic form factor. In deep inelastic scattering, you can factorize the structure of the proton, which contains a parton of momentum fraction x that is pulled out here by the interaction with the photon from the rest of the diagram, which is this is completely perturbative, what's happening at this vertex. And then when we go to this more complicated observables that arise in the deeply virtual Compton scattering or deeply virtual meson production, which are experiments that can happen here at Jefferson Lab, you have, again, another factorization of this part of the diagram where you can treat it perturbatively, and the lower part of the diagram, which is all the non-perturbative information, which is encoded in terms of these generalized parton distribution functions that are functions of the momentum fraction x, the longitudinal momentum transfer, and the total momentum transfer between the initial and the final state. And these objects are either you want to compute them in non-perturbatively with lattice QCD, or you want to extract them from experiment. You perform those experiments, you know analytically what's happening in this part of the diagram, you compare your result with your theory, and you can obtain the generalized parton distribution function or the parton distribution function or the form factor from experiment. And as you know, there are facilities that, such as Jefferson Lab, the electron ion collider, even the LHC, where these objects are playing an important role. And here's an example for you to see the determination of the parton distribution functions from experimental cross-sections, where you have the theory and you have the unknown objects that describe the hadron structure. You compare experimental results to your theory, and you can obtain, through global fit analysis, the parton distribution function. So this is a collaboration that determines these parton distribution functions from the lattice NNPDF, and is one of them that does this. And so here you have quark distribution functions. What do I have here? I cannot see. So these are the polarized parton distribution functions where the target is polarized, and this is the unpolarized version of them. Just to get an idea of what's going on. And I have to point out that there are many collaborations that do these extractions from experimental data. And if you look at this ratio of the results that various collaborations get, the NNPDF or CT and MMHT and so on, you see that there are disagreements between them, and the methodology that each one of them is using produces slightly different results. And at small x, you have more of a universal agreement. At high x, you have pretty, I don't know, significant disagreements between various collaborations. Here, for example, you can see that these experimental extractions are not always on top of each other, and there are areas where one can improve. Now, in the case of the GPDs, this extraction from experiment is a bit more complicated than in normal parton distribution functions. And these complications arises from the fact that you are after a function of 3 variables plus the renormalization scale, x, y, z, but what you measure experimentally is a function of 2 variables, c and t. And this reduction in the dimensionality of the 2 of the unknown function and the known experimental result causes you to have the so-called pseudo GPDs, which means that you can add arbitrary function to some smooth GPD that you get, and you get exactly the same experimental results. There are flat directions in the optimization of your unknowns when you condition them to the data. And that is a limitation, I would say, for experiment where Lattice QCD doesn't have it. Lattice QCD computations can actually determine these generalized Parton distribution functions as a 3-variable function, not projected, and can be used in conjunction with experiment to actually determine those unknown functions. So now let me get to the generalized Parton distribution functions and see what they are, and then try to discuss how you can compute those things in Lattice QCD. So if you open the textbook for describing generalized Parton distribution functions, or even Parton distribution functions, you will realize that they are determined as matrix elements, and this, I have a typo in this formula here. I'm missing a U bar, and there is a U here that I'm missing. In any case, so these are matrix elements of the proton with quark bilinears, just like the interpolating fields that we were, or the currents that we were writing before, but you see that the quark and the antiquark are different locations. And this omega minus is a direction on the light cone. So this is quark-antiquark fields that are separated by a light-like distance. And of course, you have this W in the middle, which is a Wilson line. It's a path-ordered exponential of the gauge field, just like the links that we have in Lattice QCD. But its direction is not along any x, y, z. It's along the light cone direction. Is the direction on which the light propagates on Minkowski space. Now, how can one compute those things in Lattice QCD? And the answer is through the so-called operator product expansion. One can look at the moments of these generalized Parton distribution functions, which are weighted. You weight expectation, the generalized Parton distribution function with powers of x to the n. So these are the moments, and one can write down an expression for these moments. And there is a very interesting property that the dependence on xi, this longitudinal momentum transfer variable, is polynomial. That's an interesting property of generalized Parton distribution functions. But one can show that this object here, which is the moment, can be computed as a nucleon matrix element of these operators that we wrote down in the end of the last lecture, which is quark-antiquark fields on the same point in space-time. There is no light-like separations anymore, but with a gamma matrix and a string of covariant derivatives. So these operators in the continuum have a certain spin that grows every time you put one more derivative, and have a dimension that grows as you add more derivatives, because you have one power of length going in the denominator. These are the so-called twist 2 operators, because the twist is the spin, the difference of the spin and the dimension. And every time you add one more derivative, you get one more value. One spin goes up by 1, and the dimension goes down by 1. And it turns out that these operators or these generalized Parton distribution functions determine the high energy scattering experiment when the momentum of the hadron is very high. In other words, when the hadron is propagating very close to the light cone. So the simplification of the generalized Parton distribution functions, these are the regular PDFs where the initial and final momentum is the same. These are the normal Parton longitudinal momentum function distributions. And they are, again, their moments can be related to local matrix elements of these twist 2 operators with a string of covariant derivatives and the gamma matrix. So one way that Lattice QCD could give some input for the determination of PDFs or GPDs is through computations of these kinds of matrix elements on the lattice. And we described the techniques of how you do it. We also talked about the normalization, and it turns out that those operators are tough to renormalize, except for the first few moments. So up to the third moment of the unpolarized PDFs, you can actually do the calculation on the lattice. Beyond that, you cannot. And therefore, Lattice QCD, it seems, that cannot produce the full X dependence of these distribution functions. But we would like to find a way of doing it. And in fact, there were certain developments in the recent years that produced a technique that allows us to go beyond the moments. So I don't want to spend a little bit more time, but I want to give you a very brief understanding of what the, let me get rid of this first, maybe put it down. So what is the basic idea? So on the lattice, we can compute quark by currents with quark and the quark field separated, but it has to be along a space-like direction. This is where we can easily compute matrix elements, and it has to be in a long space-time direction, because if you have temporal directions, then the weak rotation that takes you from Minkowski space to Euclidean space is not quite as transparent. So you can easily do separations along spatial directions, but you cannot do any easily separations along the time direction. So the basic idea comes from Zedong Zi, where he realized that if you have a space-like separation of a segment, and then which you write down on your lattice, and you do a matrix element of a proton, but now a proton that has a very high momentum. So once you go now to the rest frame of the proton, this space-like matrix element in the lab frame that we are doing the computation gets rotated, Lorentz transformed into a matrix element, a separation that goes along the light cone. That is the negative, the C minus direction of the light cone, that's C plus. So this is precisely the separation that you need to define the PDFs. So the idea was that if you take a lattice calculation with a space-like separation in quark-antiquark fields and do that with a proton that has a very high momentum, in effect, in the frame of the proton, you are computing a matrix element that is exactly what you wanted, quark-antiquark field separated by the C minus direction. And that was the idea of how to proceed and avoid to do computations of moments. Now, this idea has various twists and turns. One, I just want to flash this. I don't have time to spend more. There is additional, similar ways of doing the same thing that various people came up. Sang-Wei Chu, who is a theory group director, had this proposal of the so-called good lattice cross-sections. And the main idea here is to, again, you always have to have this momentum, large momentum P. You compute a matrix element that is a non-local operator Z, which has some separation Z between the parts of this operator. But this operator is a more complicated operator. It has a meson-like operator here, psi bar psi, separated by another psi bar psi. It's as if the proton interacts with two currents. Zhang Wei and collaborators figured out that one can do this computation on the lattice and then factorize it into a PDF and some known perturbative kernel. And that's why they call it the good lattice cross-sections, because this is exactly like a cross-section that you calculate, that you measure experimentally, where you have the PDF factorized out of the perturbative part of this diagram. So these are straightforward calculations, but they involve 4-point functions, not 3-point functions as before. So let me try to elaborate a little bit more on the basic G's, Zedong G's idea, which we have here at Jefferson Lab. Anatoly Radyushkin made it, modified it, and in my opinion makes a lot more sense. Actually, no, it's not. That's not the first statement. You can get to the same physics with a different from a different angle, let's say. Instead of thinking of boosting of the hadron to infinite momentum frame, you think about it in terms of Lorentz decomposition. So you look at the general matrix element of the proton with a quark bilinear that has some separation z. And you want to make this separation z to be space-like, because you can do these kinds of calculations on the lattice. But now, as we discussed, every matrix element of this kind admits a Lorentz decomposition. In other words, it can be written in terms of Lorentz invariances. For example, this object here has a Lorentz index alpha. So in order to write down its Lorentz decomposition, you have to figure out what kind of vectors I have in my problem, what kind of invariances can I make. And in this particular case, you have the momentum p of the hadron is the only vector, and z, the separation of the quark and the quark fields, is the other vector. So you can have a term that is proportional to p and the term that is proportional to z, and then the rest are going to be Lorentz invariant quantities that are made out of p dot z, z dot z, which is z square, and in fact you would say p dot p, which is p square. But these matrix elements are on-cell matrix elements. P square equals the nucleon mass, so p square drops out. It's not really a dependence because p square is constant. So that is the matrix element that has this particular Lorentz decomposition, which you can compute on in Lattice QCD, no matter what A or alpha, or this index, or Z or P you use. And you can use the convenient, whatever it is convenient for the lattice calculation, but in the end of the day, you are going to get these Lorentz invariant form factors that characterize this matrix element. So now, if you go and say, well, what is the PDF definition? The PDF definition wants you to separate the quark and the quark fields by the minus light cone direction, and you want to have the proton momentum in the P plus direction, and you want to have the gamma plus matrix inserted into the matrix element. So if you use these kinematics, let's say, that define the PDF, you immediately realize that this thing, which you would call the PDF up to a Fourier transformation, is given by this invariant form factor MP. But this MP is the same for all possible kinematic choices due to Lorentz invariance. So instead of trying to do this calculation on the light cone, where I cannot do it because I am working in Euclidean space, I will do this calculation in Euclidean space, but I will choose Euclidean kinematics. I will put the Z to be in the space-like direction along the third direction. I will put the momentum P along the same direction. I will choose the gamma 0 or gamma 4 in Euclidean space as my matrix, as my gamma structure. And if I do that, I will take the Lorentz decomposition formula that I had before, that I wrote here. How do I go back? Go back. Go back. Because the index alpha is the gamma 4, this term drops out because the fourth component of my z, the separation, is 0. Actually, I write it the fourth component, time component, I write it first because I think of it as Minkowski kinematics at this point, although I am working in Euclidean space to get this calculation done. So the z is 0, so this term drops out. And if I look at the Lorentz decomposition formula that I had before, I normalize by this P0, and I get my MP, which is the form factor that is related to the PDF. And in fact, I have to do a Fourier transformation given my definition of the PDF. If you remember, you have to do a Fourier transformation in order to go to the momentum fraction x. So this MP factor, Fourier transformed, gives me a PDF. And forget about this for a moment. This is there because I did the calculation at some finite z, z squared, which was not 0. Light cone requires you to have 0 here. So for that reason, this object is not called a PDF, because PDF formally is defined on the light cone. It's called the pseudo PDF because I have this additional z squared dependence. And the understanding is that I have to take the z squared to 0 limit in order to obtain the full PDF or the light cone PDF. However, we have a problem. In the limit of z squared going to 0, you have divergences. So this limit is not trivial. You cannot take it easily. But what one can show is that this singularity, which is called collinear singularities, if you have studied cross-section factorization theorems, this is the same. The source of the singularity is the same as what you call the collinear singularities in this context. This can be factorized all into a perturbative coefficient, which is, you can calculate it analytically, and the MS bar renormalized PDF, its Fourier transformation. So this Q is the Fourier transformation of the PDF that you are trying to get. And to this factorization formula, you have corrections that are order z squared times lambda QCD, which is the fundamental scale of strong interactions. And these order z squared terms are called the higher twist terms, because the leading contribution, which is the PDF, is the twist 2 contribution, which is the leading contribution, and this is the subleading. And if you have looked at the high energy scattering and factorization theorems, you have heard that there is 1 over q squared power corrections, which are called higher twist contributions. So this is exactly the same thing as the power corrections that you have in perturbative QCD studies of high energy scattering. Okay, so the lattice calculation, if you wanted to proceed, would be to compute these matrix elements the way we discussed, to get this object here. You use this factorization theorem. This is a known function. You can invert this relation and obtain this object, which you can there Fourier transform and get to your PDF. And all this work has been done in various different ways. And let me make a remark here about this original G idea of this high momentum, infinite momentum limit of the lattice calculation, you would obtain the PDF as a Fourier transformation with a slightly different combination of variables here. In the Z language, you would you could compute an object by integrating along this red curve in this nu and Z square plane. And as you take the momentum of going to infinity, which appears here, this argument has to go to 0 in order to go to the light cone. This integration curve will open up and touch the light cone, which appears at Z square equals 0. This is Z square equals 0 is the light cone. Okay, so in the case of the way that I describe things in the pseudo PDF language, you're performing a Fourier transformation at some fixed Z squared, which is a distance from the light cone. And you want to take this limit of Z squared going to 0 in order to obtain the light cone PDF, which you can do by doing this matching procedure and removing the collinear divergences. Now, if you ask the question, what is the the dependence of this matrix element that you compute on Z square? There is a logarithmic dependence on Z square, which one can, I don't know if I had the opportunity to tell you what this is, but so one can analytically determine this dependence on Z square, and it goes by a name which is famous, the Diglap evolution, as it is called, which tells you what is the scale dependence nu of the PDFs that you want to obtain. If you have normalized PDFs at a particular, in MS bar scheme at a particular scale mu, their dependence on the scale mu is computable in perturbation theory, and this is known. And this result is going by this name of Diglap evolution, and this, which can be written. So this evolution of the underlying PDF dictates an evolution of the lattice matrix element with respect to Z square. And this object here, B, is called the Altarelli-Parisi kernel, which it has a very simple form. All I'm saying is that this is exactly known from perturbative QCD how this works. And here I wanted to quickly point out that if I perform this lattice calculation and compute this object as a function of m of nu, which is the Fourier dual of the momentum fraction x and Z square, I get a bunch of points, and I have color coded all these points with respect to the value of Z square. Now I claim that I know how the Z square dependence should go from perturbative QCD, and I can now move all my points according to the equation that I had before, and you see that everything now falls on the same universal curve, more or less, at some fixed Z square. So all I'm saying is that this analytic argument, this analytic perturbative QCD result that goes by the name of Diglap evolution through the Altarelli-Parisi kernel dictates the Z square dependence of the lattice calculation, and I can actually observe it by doing this calculation on the lattice and evolving my points according to this equation. And the same thing goes for the imaginary part of this matrix element, where you have a bunch of points color-coded by their value of Z square, and I can evolve it to the same Z square, and now you see that all these points fall on a more or less universal curve. Okay, now there is a question that I avoided discussing up to now, and this is the question of UV divergences. As we discussed, every lattice calculation of a matrix element it has to be renormalized in order to take the continuum limit. And if we look at perturbatively what happens in this Wilson line matrix elements of quarks separated by some distance z, this is a Wilson line. It has gauge fields, so you can have a propagator that goes from one point on the Wilson line to another point on the Wilson line. The self-energy, you can have this diagram that goes from the Wilson line to the quark propagator and this brother on the other side. And if you compute those diagrams for z being a space-like distance, you get something that looks like this. So if I take the continuum limit, this exponential here with the factor of the lattice spacing in the denominator at some physical distance z will wipe out my matrix element. So if I do not remove this term that appears from the calculating these diagrams, if I don't remove it from my lattice matrix elements, I cannot take the continuum limit. The good thing is that unlike the twist 2 operators that I described before that have mixing problems, this factor here is completely multiplicative and it depends only on the value of z, the separation. And that makes it easy to eliminate it. If I now take a ratio of this object that I want in the numerator divided by the same object, but now at zero momentum, nu is p dot z, as I told you. So this multiplicative factor will cancel exactly in the numerator and the denominator, and it will leave you with the light cone or this curly M object that contains the light cone PDF in it. And in the case of the, when I insert the gamma matrix, there is this normalization condition that holds, which is the fact that the charge of the proton is 1. And it is engoated into this matrix element at zero momentum and zero separation. The value of the matrix element is exactly 1 from charge conservation. Now, once I have eliminated all these issues with the divergences, I have obtained this object that is universal, and it has a smooth continuum limit. If I take the continuum limit, I will get the universal result, which I can then use to factorize the PDFs, their Fourier transform, with a known perturbative kernel, and I have to account for these corrections that are the power corrections. And if I have this result, this matrix element computed, and try to invert this formula by doing fitting or inference, as it is a more proper name of the procedure, I am going to obtain the PDFs. And this is the method that we're currently using in order to obtain X-dependent Parton distribution functions. You measure this on the lattice, and then you invert this relation to get the answer. Now, you might ask the question, what's happening with the moments of the PDFs that we have been talking about? This is, if you look at the Taylor series expansion with respect to this variable nu of the matrix element that we compute now on the lattice, it is, you can show that it expands into a bunch of perturbative coefficients that are known analytically, powers of z, and these matrix elements that are the moments of the Parton distribution function. So if I look, and so these factors of z here because if you remember, if I have the formula down here, if you rewrite this matrix element in terms of the moment of the PDF, you get these strings of p's in front of it. And these p's contract with the z's and creates powers of nu. So these terms that you see here become the Taylor series expansion coefficients of this function here in terms of nu. And the coefficients of this Taylor series expansion are the moments of the PDFs. And in other words, that I can write down this formula by taking derivatives or doing the Taylor series expansion, accounting for some factors of I that show up, and take the nu square equal to 0, the nu equals 0 limit. I will get the perturbative coefficient, which are the moments of the kernel that I have, this perturbative coefficient that converts from the MS bar PDF to the pseudo PDF, and then I have the moments of the Parton distribution functions. So if I study the small nu dependence of this matrix element, I can obtain the moments. And in order to do that, I don't need even a high momentum. The nu can be small, so I can have a small value of z and a small value of p, and I will get a small nu. And all this is all I need is the small nu behavior of this matrix element in order to obtain the moments. And in this case here, apart from numerical, I don't know, accuracy problem, you can actually obtain any moment you want. Of course, obtaining Taylor coefficients from a function becomes difficult the higher the order that you want to go, because the precision with which you have to obtain this function grows fast. Anyway, but in principle, you can get moments, and I have done this computation here where these shaded bars are moments extracted many years ago from this collaboration, Lattice QCD collaboration, that obtained these moments in this quenched approximation that I'm working on here with some particular value of the pion mass. And you get a lattice calculation as a function of the scale nu of the moments extracted by the pseudo PDF approach, and you see these points converging to the result of the QCDSF, meaning that the computation that I did on the lattice with this new method and the computation that I could do with the old method, calculating the matrix elements of the twist 2 operators directly, are the same. Now, so what else do I need to say here? So let's look at the analysis of the problem. So in reality, when I do a lattice calculation, I compute this matrix element that I want at some fixed lattice spacing with some value of p and z for the hadron. Now, the leading contribution to this result that I get from the lattice is the continuum function of the variable nu and z square, but it is contaminated by several other things. Because of being at the finite lattice spacing, you have things that are proportional to the lattice spacing. As you take the limit of the lattice spacing going to 0, these terms are going to vanish, but they are there. So you have an infinite tower of a to the n contributions that contaminate the continuum result at any given lattice spacing. So you have to do an extrapolation. You have to do several lattice spacings so that you can extrapolate away these contributions. Now, the continuum result by itself is also not clean. So it gives you the perturbative kernel that we talked about. It gives you the PDF. This is the leading twist, the thing that you are after. But it has this power corrections that you have to take care of. So in order to analyze the lattice data, you have to parameterize all these effects. and have the calculation done for several lattice spacings and for several values combinations of P and Z, and you have a complicated inverse problem to solve. Given the lattice results, parameterize the unknowns, which is the PDFs, which you want, and all these nuisance terms that are representing the contaminations. And how do you solve this, this inverse problem? One methodology is using the so-called Bayesian inference. What do you do there? You have a likelihood function, which is what is given a model that describes my unknown functions, and this model can be whatever you want. I will call this model theta, the parameters of that model theta, and I will call my data ML. So this likelihood part of the posterior distribution that I want to do. So what do I have to compute? I want to compute the probability of the parameters of my model to be what I infer them to be, given the data, plus some prior information. This is the I here stands for prior information about what my unknown functions might be. So I have these two ingredients. I have the lattice data, and I have the prior information about what my unknowns have to be. And I want to find what is the probability of these parameters to take certain value that describe my unknown functions. That's the posterior distribution. So by Bayes' theorem, this posterior distribution can be written in this form. This is the likelihood function, which tells me what is the probability of my data given a certain value of the model parameters, times the probability of these model parameters given my prior information. So this is the critical part on the numerator. The denominator is just a normalization constant, which it doesn't play any role because it doesn't depend on theta. So by setting up an appropriate prior probability for my model and my likelihood, which is basically chi-square, you all have done a fitting, then I can obtain the posterior distribution, which gives me the probability of the parameters of my model given the data and the prior information. So that is the methodology that one uses in order to obtain the PDFs. So if you do that, and I'm not going to write down the details of how this fitting goes, but here is an example of the unpolarized PDFs that was done in a particular, it was done in an unphysical setup. And the unphysical setup is I have a heavy quarks. The quarks are not light as it is in QCD, but for computational reasons, I use quarks that give me pions that are pretty heavy, 450 MeV. They are more like kaons than pions. And this is the computation you get from the lattice by doing this Bayesian inference methodology that I described. And this is the PDFs that you get from phenomenological. Now, there is a hump here that is more likely due to the fact that I have heavy pions. And because this distribution is normalized, if you have a hump here, you have to have a dip of. Now, one thing to note is because all these calculations are done on the lattice and the range of momenta that I have for the proton is finite, I have a natural cutoff that is somewhere here of sensitivity. So my lattice data will not have any sensitivity beyond this particular value of x because I have a finite range of x, of nu, the Fourier dual of x. Okay, so now here's another example of the same type of calculation. Now I have this is the PDF that gets extracted, and this is a busy figure because it tries to give you not only the leading PDF that you get, but also all these contaminating factors to see how big the contaminations are. And these are the primary data that I have from the lattice. So these are the points of this curly M that I told you about. And this is the how this model that I have fits the data. And this line here is if I only isolate the leading twist, the one that is responsible for the PDF. And this is the full model, how it describes the lattice data. In this case, it does a pretty good job. So here is another example of the so-called helicity distributions where you have a polarized proton. And in this case, the lattice calculation, although it's done in a physical setup, it is in very good agreement with the experimentally extracted PDF. And again, this is how the lattice, the model describes the lattice data. Finally, the so-called transversity distribution. Again, we have a good story here that the lattice data describe the phenomenological extractions very well. Now, how much time do I have? Almost done. Huh? So let me very quickly, what should I say? There are some modern techniques that go by the name of Gaussian processes where you parameterize the unknown functions not as a known functional form, but is a so your unknown function is a bunch of values on a grid. So you have many more parameters in the model than when you have with normal parameterizations of an unknown function. So you, so I don't know if I should. So this for you that you might want to go into this, the so-called Gaussian processes is a non-parametric way of describing unknown functions. And if you basically describe them as a distribution from a Gaussian distribution with a particular covariance. So your unknown function, your prior information for the unknown function is given by a distribution. It's not by a set of parameters. And because this prior information is chosen to be Gaussian and your likelihood is Gaussian, you can analytically solve for the posterior distribution. And you don't have to do non-linear minimizations in this particular case. And here is an example of how this technique works. You have, these are the input data points, and this is the extracted PDF using this Gaussian process methodology. Let me not spend too much more time here. Just wanted to flash you that the generalized Parton distribution functions are exactly the same types of matrix elements that I described before. The only difference is that the initial and final momentum of the proton are different. And because of that, now I have many more vectors. So the Lorentz decomposition becomes a complicated thing with 8 invariant amplitudes that you need to extract. Fortunately, you have enough constraints by computing several 3-point functions with this index mu changing, the spin indices of the proton, which I didn't write, changing, initial final momenta changing, and you have enough constraints to extract all these invariant form factors. And from them, you can determine the generalized Parton distributions, which are known as the H and the E. So all I wanted to point out in the end is that after you've done all these complicated calculations, you end up having an extraction of generalized Parton distribution functions with their X dependence explicitly known, not very well known, but it's a first step in actually doing these calculations. They are early stages, but you can get a determination of the generalized Parton distribution functions, both their X, C, and T dependence. All the 3 variables can be captured. Okay, So I will stop here with this slide where I'm trying to tell you that one can do computations about hadron structure to obtain parton distribution functions, generalized parton distribution functions. We have a well-known technique. We know how it works. It's complicated and very expensive. And I would like to allude to Archimedes, where when he discovered the lever, the trick of the lever, how do I get rid of this so that you can see this nice picture here. Archimedes is known to have said, when he discovered the lever, that give me a place to stand and I will move the earth. And I think for this kind of problem, I feel in a similar way. I know how to do it. However, I don't have a big enough computer yet. Okay.
Thank you very much. Question?
Yeah, so you displayed some results, I mean, very rapidly for the general parton distribution functions and the PDFs. But do you have any like good like form factor results, both for the like any like either proton?
Yeah, actually there are the form factors are very well studied, and they are not. So I didn't have time to talk about them. So here is an example of our extraction of the form factor. Of course, this is again an extraction out of our lattice computation of GPDs, because the form factor is a limit of the GPD.
Right.
So these are not state of the art of form factor calculations. The state of the art are at physical pion mass and in the continuum limit. And but this is a typical picture. So once you start, you see the scatter of the points that you see here. This is an effect of a single lattice spacing calculation that we have. But there are people that have performed the same calculation for multiple lattice spacings, extrapolated the continuum limit, and you will see that you get a nice smooth curve. And in fact, in the recent days, the agreement with experiment is pretty high.
Okay, yeah. So has anyone used this to extract? I mean, you said you have the GPDs in terms of like X as well, right? So, or in terms of, I mean, maybe you can get that in terms of Q squared and then use that to get like a proton radius prediction.
So the generalization of this of the form factor is the so-called generalized form factors, which are parts. What are the generalized form factors? If you go here, and if you take the moment, if you take the Taylor series expansion with respect to nu of this generalized amplitude that comes in the Lorentz decomposition of the GPD matrix element, then it expands in powers of nu this way. The leading term is the form factor. The second term is the moment, is the second moment, but or third moment actually in the counting that it's 3 that the index goes here, but it's the second power in nu. So which is made out of these objects that are called the generalized form factors. So the first index here is this power plus 1. The second index here is the power of xi that it's coming from. So this thing inside the parenthesis is a polynomial in xi squared that terminates. So the power of xi can never be bigger than that. So the same thing happens here. So these are the generalized form factors, which are functions of z squared and t. So z squared is the Lorentz invariance that appears here. And these generalized form factors we can extract by looking at the Taylor series expansion of the lattice matrix elements of these lattice matrix elements. And we have actually extracted those. And okay, where is it? Oh, I'm going the wrong direction. And this is an example of this extraction. Now, you see that the scatter now is bigger. I have to rely on bigger momentum for the hadron. That gives me bigger lattice spacing errors. So I have to deal with it and do some fit that is as good as I can. If I had multiple lattice spacings, all these errors will go away. And how do I characterize this generalized form factor? I can characterize it by the intercept here. And if I do a dipole fit of all these points, I can get the dipole mass, as it's called. And we've done this for several of form factors. You can see it goes up to the x cube, the A4 term, and we have extracted the second coefficient in Xi here for the H and the E. And here is the dipole mass that is associated with these form factors. This is a relatively old paper now. It's 2 years old. So that's the generalized form factors. Okay. I don't know if you were asking about this.
In effect, yeah. Yeah, I also just have one last question. Can you go back to the Pion PDFs, specifically the ones against like X?
Where?
Yeah, sorry, the Zoom thing was blocking slide numbers, so I don't know. But
You
like,
want,
sort of way back.
is this?
Yeah, exactly. So wouldn't you expect the Pion PDFs though to go to, like,
This is not the Pion, it's the Nucleon PDF.
Oh, okay.
But it is done with a Pion that is heavy.
Okay, okay.
And if you wanted to see something about Pion PDFs, I can go down here. Oh, sorry, I want to do this. I can go here and, oh, no, this is not the Pion PDF. I don't have the Pion PDFs. Sorry, I do have, we have done this with Pion PDFs, but here is a crazy calculation, in my opinion, that it shows you the potential complementarity between lattice QCD and phenomenology. So if you try to calculate the gluon helicity distribution, which is covered here, which is basically a distribution of the gluons inside the proton when the proton is polarized, and you do the extraction from experiment with global analysis, you find that there are two possible functions that describe the experimental data. One is this green, and the other is this red. Now, this is a notoriously difficult calculation for the lattice. Okay, so this is the helicity distribution, this is the Pion distribution. Okay, so this is a notoriously difficult calculation, and you see you get very bad noisy data. These are the blue data points, are the lattice data, but they are all in the positive direction. And if you combine now the lattice data with the phenomenological results, this red branch that was sitting down here now all of a sudden becomes positive, and you don't have this, I don't know, two possibilities for describing the experimental data. So you have now two consistent solutions to your experimental problem. Now, here is the Pion distribution. If you can see, again, we played this game by taking lattice results together with experiment and a very limited number of lattice results. And you will see, if you look at this red line, it is a reduced uncertainty. So experiment only has this bigger uncertainty. You combine it with a little bit of lattice data, and you get a reduced uncertainty in the extraction. So although the lattice calculation did not extract a full Pion PDF, there's little input, few values of variable nu and z used into, together with experimental results, it reduces the uncertainty of the extraction for the Pion PDF.
Very nice, thank you.
More questions? Anyone?